Where is that coming from? Oh, yeah. It's from me.
Or it's from you?
Yeah, I didn't have YouTube. Yeah, I didn't have. If anybody else has YouTube up, please mute it.
Oh, it's, yeah. Sorry, that was me. I forgot to mute YouTube. Oh well. Guess my only excuse is that we haven't technically started yet. You muted your Google Hangouts mic, so I can't hear what you're saying.
I said I got new headphones, but they smell funny.
Oh, gotcha.
Hey Jeff, I muted you just because you got a lot of background noise coming through.
Yeah, sorry about that.
Oh no, it's not a problem.
Should I get started?
Seems as good a time as any, yeah.
Okay. Well, I guess I'll look at the camera, I suppose. But I prepared a lesson for stability. That was one of the topics that was asked for in Piazza. And we're going to go through my notes. This is, I guess, part of a midterm review, but we're basically just going to focus on stability unless people ask questions, at which point we can answer in real time. So let me go ahead and present my screen, and then I'll go over my notes. So you guys should be able to see my screen now. I'm just going to verify that on the YouTube channel real quick. Well, there's a pretty big delay. There we go. Perfect. All right. So these are my notes on stability. I have uploaded them to Piazza too for anybody that has a second monitor and wants to follow along, but that's not necessary. So anyway, stability is the concept of a system that, well, I mean, it's stable. You can create unstable systems. They're just not very useful or practical, or they break your equipment and you have to build it again. And we have numerous examples of stable and unstable systems. You know, a stable system is, you know, your computer working in front of you right now is a stable system. An unstable system might be when you put a microphone too close to a speaker, and then you get that feedback loop, and it pierces and screeches and potentially eventually breaks your speaker. So that would be an unstable system. Most microphone speaker systems these days have limiters that would prevent that, but it is a good example. Another example that I found from the textbook was the example of a pendulum versus a inverted pendulum. So a pendulum, you know, you pick up the end of the pendulum and you drop it, and it swings back and forth until air friction slows it down to a resting point. The resting point is in the center, where equilibrium is. In other words, it's a stable system because it reaches equilibrium, the starting point. Now, if you invert this thing, and you have, and you're kind of like balancing a pendulum on its end on the ground or on the floor or something, and you tip it, it will just tip right over and it won't ever return to its starting point. That kind of implies that stable systems are periodic, but they don't necessarily have to be. I don't have any specific examples off the top of my head, but anyways, that's a pretty interesting example. Is the inverted pendulum. You tip it, it knocks over, and it doesn't return to its starting point. But let's get into some more formal or codified examples or definitions from this course, you know, the Signals and Systems course. So I have here the definition from chapter 1. We have two definitions that we work with. The chapter 1 definition is a very broad and generic definition, and it's very simple in the sense that it says, for any bounded input x of t, you have an output that is also bounded, if the system's stable. Now you can have unstable systems, at which point this statement does not apply. But if we're talking about stability, this is the definition for it. So all this really says is that if I have some signal, this signal, if it's bounded, must be less than some arbitrary point, some bound. You know, you can set your bounds wherever you want. Most often the case is the bound is just a constant. So if you plotted this on a graph, such as this right here, I arbitrarily defined my bound to be 1.5 and my signal to be just 1, a straight up 1. But if you have a curvy, complicated signal, you can define a bound that curves as well, or is some kind of envelope, such as, you know, you've seen some FM modulation type stuff in your differentials class and maybe some other courses, maybe circuits or something. And you have some carrier wave that gets modulated, and then you have a bound that's defined by the envelope. So that is an example of a bound that's not just a constant like I have drawn here. But there's, you know, the examples are endless. So anyways, this is a very broad and generic definition. If we want to skip ahead real quick, I'll scroll down to the second definition that is more applicable to the rest of this course. The second definition is from chapter 2. And all it really does, different than the first definition, is that it codifies what a system specifically is, as opposed to, well, let me scroll back up. So the statement from the first, the chapter 1 definition talks about an input and an output. It doesn't talk about a system as a whole. What's implied here is that the equation that's represented by x of t equals y of t, that is a whole system. But in the chapter 2 definition, we've codified that we want to represent the system as a whole with one term or one equation, and we just call it h of t. And that's what we do throughout this entire course after chapter 2. So anyways, this chapter 1 definition, let's look at a quick example. That I got this from the textbook. So let's talk about a system 1, you know, or a system that is defined by this equation. So y of t equals t x of t. X of t could be anything. It's just your input. And this system takes whatever your input is and multiplies by t. Well, the first thing you want to do to determine if this system is stable is, or the easiest way to determine if this system is stable, is to try to find a counterexample to disprove system stability. This takes a little bit of cleverness on your part, in that you have to think of what might break this system in a sense. So what if I just define my input to be some bounded input, and I know that x of t equals 1 is a bounded input because it never goes beyond 1, right? Because that's what it is. And I arbitrarily define my bound to be any point that's above 1. Then my y of t will always equal 1 times t. So as we increment t, it'll be that number times 1. So starting at 0, y of 0 equals 0, y of 1 equals 1, y of 2 equals 2, so on and so forth. You can see that this will go on to infinity. So y of infinity equals infinity, because infinity times 1 is infinity. If we were to, for the moment, pretend that infinity was an actual number. And that's what I wrote here. So this is not bounded, therefore this system is not stable. You can also do it graphically, which I've done here. So for each t value, I'll multiply by 1, and this will go up linearly to infinity. So you can see that it's clearly not bounded. Now, this bound I chose, and this is B prime, that's a bound for the output. So if you have a bound for the input, your bound for the output doesn't necessarily have to be the same thing, but it is some bound. All right, so example 2. This is just another example where you might not find a counterexample, so how then do you prove it? So system 2, let's take y of t equals the exponential e to the x of t. So I can't think of a counterexample that causes instability outright, because I did try a few here, but I don't think you can think of one, and that's why it was given in the textbook, because it's a system that you can't think of a counterexample. So I tried at first the same input that I tried with the first system, just a bounded input, x of t equals 1. Well, if I apply that to the system, it just goes e to the 1, and then it becomes a number. Well, my output is also bounded. What about some other number besides 1? How about 12? Well, e to the 12 also becomes some number, it's a constant. What about some bounded input that is not just a constant, such as sine of t? We know sine of t is a periodic signal. It changes, it's dynamic, but it's bounded between 1 and -1. That's the sine wave. So let's try that. E to the sine of t, and it took a little gerrymandering to zoom out correctly on my graphing calculator to find out the actual shape of this, but it's basically just a periodic signal. It's just shifted up and modified in such a way that it looks fairly close enough to this that you can see it's bounded as well. It doesn't go off, it doesn't blow up to infinity or negative infinity. Well, when you're looking for counterexamples, you want to be careful. So I had to be careful on this one. I was trying to write this out, and then I realized, oh crap, this isn't a bounded input. So x of t equals ln of t. You might think at first, oh, this is a great input to try, but it's not. It's unbounded. It grows exponentially, just very, very, very slowly. So when you stick that in, you create an unbounded output. But it's an unbounded input, so you can't use it as a counterexample. So be careful with that. Anyways, so you can clearly see that there's no counterexamples that you can use to disprove this this system being stable. So you need a new approach. So anyways, let me read this note here. Anyways, we need a new approach that lets us tests all bounded inputs all at once, so we're not sitting here for a lifetime. So what we do is, if x of t, the absolute value of x of t is less than some bound, some arbitrary bound, and this bound could be anything except for infinity, then y of t must be less than what our system is, e to the bound, or y of t must be greater than e to the negative bound. That's just because of the absolute value there. This is just another way to write that. So that's how you prove that. Now this number, whatever this number is, could be anything, as long as it's not infinity. And if you're bound, the one that you choose is not infinity, this will always return some just a normal random number, a function. So anyways, if you have some bounded input and you get some bounded output, that means the system is stable. Hopefully that makes sense. If not, it'll make a little bit more sense when we actually codify it with the second definition, the chapter 2 definition. So we have two definitions, one in continuous time and one in discrete time. Continuous time is just systems that you know, are analog or like in real time type things, where a discrete time is something that is sampled, such as a digital system, a computer, for example. So anyways, the definitions are fairly similar. So for stability for continuous time, you take the indefinite integral of your system to its absolute value, and that must be less than infinity. So in other words, the indefinite integral must converge to a, to an unbounded, or to a bounded result. Same thing with discrete time, except that we don't have integrals in discrete time because they're discrete points. So we take the sum over infinity, which is the same thing that an integral does. An integral just does it ad infinitum. So same definition. It must be less than infinity. All right. So let's get through some actual examples. So I have a couple examples that were from practice problems throughout the course. Most of them were from week 2, I think, and maybe one from, yeah, they're all from week 2 basically. But I did add some other examples that weren't in the practice problems, so that we can see something else besides what students might have already seen. So anyways, I started off with the practice problem 2.28a. where we have h of n defined as 1/5 to the n power times the unit step. So we just stick this expression inside the definition, which I've done here, and then we test to see what its output becomes, to see if it's infinity or not. And that's really the only thing you have to do, is just see if it's infinity or not. If it is infinity, the system is unstable. If it's not infinity, then the system is stable. So the way you actually go about doing that is you have your infinite sum goes from negative infinity to infinity times the unit step. The unit step modifies how many terms we need to sum up, because the unit step is 0 everywhere except starting at 0 to positive infinity. So all the negative infinity values can be discarded. So we can go from the infinite sum starting at 0 to infinity. That puts this whole thing into a form where we can use the geometric series, which we learned in week 1 from the chapter 1 key concepts, which we have. I need my hand tool. Nope, I need my select tool, which we have right here for k equals 0 to infinity. The exact same form, alpha is less than 1, and our alpha in this case is 1/5, which is less than 1. So we can then convert it to that geometric series form. Now 1 over 1 minus 1/5 equals a number, which is clearly not infinity. Therefore, this system is stable. Now, the second example is from problem 228 in the textbook, part F, where we have h of n equals negative 1/2 to the n power times the unit step, plus a second term, 1.01 to the n times the unit step that's time reversed. So here we have two terms. This is a superposition of two systems, which means that we can use the distributive property of systems and evaluate stability for each term separately. So where I got this from is from our chapter 1, week 1 concepts. And let me scroll down to find it. I'm sorry, it's from chapter 2. Yeah, here it is. So your chapter 2 distributive property, this is talking about systems interacting with each other. So we have some input being applied to a system that has two terms, which is really just two systems in parallel. So that means we can evaluate each of these separately using the stability definition. So anyways, that's what I do. So here I just rewrote the problem, and then I broke it up into two separate problems. So first, let's do the first one, which I've named h1 of n, which is down here. So I rewrote h1 of n, which is the first term in our problem, and we just need to solve this and see if it's infinity or not. So again, it's pretty straightforward. We're using the geometric series because we have a k equals 0 going to infinity. We have an alpha that's less than 1 to the n power, and therefore we use the geometric series. And this again just evaluates to a number, number being not infinity or less than infinity. Therefore, that part of the system is stable. So now we need to test the second term, which I've labeled h2 of n. So h2 of n is 1.01 to the n power. So first, you might notice that this is higher than if this is alpha for a geometric series, this is higher than 1 or bigger than 1. So we might not be able to use our geometric series right away, but fear not, we will be able to use it in a minute. Then we have some weird step function that we have to consider as well. So I thought I rewrote this to make it clear, but basically this is just a time reversal. So this is really n plus 1 quantity times -1. Does that make sense? So it's a time reversal, and that means we have a unit step going backwards in time, and we only look at the n values that are negative plus 1 positive 1. And that makes more sense when I show you the next term. All right, so the next term here, I just rewrote it. This unit step goes from negative infinity to 1. So So how do we get this into a form that we can use the geometric series? Because right now we can't use the geometric series still. Our geometric series goes from 0 to infinity. So the first thing we do is realize that we can invert the argument to then take positive values of k. And then we can plug and chug to use the geometric series and then finally get just a number, which is clearly not infinity. So if it's not clear, let me scroll down and show you how we did that. I have a message here, but wait, what happened here? What happened between these two terms? How do we go from here to here? It seems like magic at first. Well, if you remember how exponents work and inverses and stuff, if we have a to the -1, that equals 1 over a. So if we're doing mostly all negative values of k, like we are here, well, we can just invert it and then start using positive numbers of k. So that's what I wrote here. Why don't we just invert the argument and take instead positive values of k, and this will then allow us to use the geometric series. So hopefully that makes sense, and this is the key right here to explaining that. Now we have one more step that we have to take care of too. So we inverted the argument to allow us to use positive values of k, but you see here we have one negative value of k still. So we need to handle that one term of this infinite sum. Remember, this is just a bunch of terms added together. So what we do is just explicitly write this one term and then write the rest in this sigma notation. So I have this one explicit term here. So we have this argument where n equals -1. N equals -1. And this evaluates to just a number. Then we have the rest of the infinite series, or the infinite sum, starting at k equals 0 to infinity, because we already took care of k equals -1 right here. So hopefully that's clear and it makes sense. Then we use the geometric series on this part, and then we add those two terms together. So this number right here, if you stick it into a calculator, equals 1.01. And that's what I wrote here. And then this number, when we apply the geometric series, it's this number here. We add them together, and you can put them in a calculator, and it'll spit out an actual, it'll just be a constant, which is clearly less than infinity. Now we have one more step, and that's to put both our systems back together, where our original problem statement was just a single system made up of two subsystems. And since both were stable, the whole system is stable. So that's that problem. Now let's see what happens when we have a problem that is unstable, because we've done only stable systems so far. What does it look like when we solve a system that turns out to be unstable? Well, I used problem 228C from the textbook. It wasn't part of the practice problems or anywhere else in the course, so this one I had to do myself by hand, but it's still a pretty straightforward and simple problem. So we have h of n equals 1/2 to the n power times a unit step function that is time reversed. So I stick this whole expression into the definition for stability. And then the first thing we do is we take the unit step and we modify our k values. So the definition normally goes from -infinity to infinity, but the unit step says, this unit step, which is time reverse, says that this system is on for only negative values of n, but it's turned off at 0 and is off for all positive values of n. So we write that in our k values. So what I just said was that at 0, it's on at 0 and it remains on for all negative values of n. So k equals 0 to -infinity. And then we have the normal stuff here that you normally see for your geometric series. But how do we solve this? How do we apply a geometric series to something that has a negative infinity? Well, you can do the same thing that I did on the previous problem and invert the argument and then try to apply the geometric series. But wait, we run into a problem. When we invert 1/2, it becomes 2. So rewriting that as 2, we cannot apply the geometric series to this problem because alpha is greater than 1. Therefore, this problem does not converge. There is no geometric series. It does not converge. It diverges. You can plug this into a calculator or into like a graphing calculator and graph it and see that it explodes to infinity. So when you evaluate this expression over infinite terms, it becomes infinity. So this can be done by inspection, or you can actually graph it. So graphing calculators give you a nice smooth plot, but you just remember that this is a discrete problem, a discrete time problem. So just remember that you're taking samples at arbitrary intervals. But anyways, when you plot 2 to the n, it is an exponential. It goes off to infinity, and then just take a point, you know, equal increments, and you can see you're blowing up to infinity. That's stability for discrete time. So let's get into stability for continuous time. So the first couple problems I took from the practice problems, then I did a couple more that were not in the practice problems, so you can see some additional examples worked out. But it's basically the same exact thing that we're doing, except for we have to deal with an integral instead of a sigma notation, a sigma infinite sum. So example 229a from the textbook is h of t equals, and you see we use parentheses instead of brackets, so that tells you we're working in continuous time and not discrete time. But h of t equals e to the negative 4t times a unit step t minus 2. This unit step here says that our system is off up to the point t equals 2, and then is 1 thereafter. And then you multiply that by the rest of the expression. So we stick this into our definition for stability for continuous time, which means that you just stick it inside of an integral from negative infinity to infinity, and then you just plug and chug. So it's a fairly straightforward, simple integral, except that first we want to handle this unit step. So what did I say before? It starts at 2 and goes on to infinity. It's 0 otherwise. So that just modifies our limits of integration. So we start at 2 and go off to infinity for our limits of integration here. And then e to the negative 4t, that's a very simple integral. It just becomes negative 1/4 e to the negative 4t. Evaluated at these 2 points, 2 and infinity. So I basically just plug that in. So I have my 1/4 here. Here's my e to the negative 4t evaluated at infinity, minus e to the 4t evaluated at 2, t equals 2. Plug and chug. E to the negative infinity actually returns a real number, and it comes out to 0. And you can verify this on your graphing calculator. There's other proofs too, but plugging and chugging, we have 1/4 times 0 minus 1/4 times e to the negative 8. And I notice that there's more negative signs than I said with words, but anyways, this comes out to just a single number. You plug this into a calculator, it is this number right here times 10 to the negative 5, which is clearly not infinity. It's less than infinity. So this system is stable in continuous time. All right, example 229d, which is also from the practice problem from week 2. This is h of t equals e to the 2t times the unit step minus 1 to minus t. So this unit step is modified. It's also time reversed. So first thing you might notice is that this is a positive exponential, meaning that by itself it would blow up to infinity, but it's modified by the unit step. We're going back in time, so we're only going to be using values that are of t that are negative. So this will actually converge to 0, as if this said e to the negative 2t, because the t is negative, except for one of our terms. So anyways, we stick this whole thing inside our definition, like I did here. The first thing we're going to do is have our unit step modify our limits of integration. So let me rewrite this real quick. That's what this little arrow in this note here says. So u to the minus 1 minus t is really just a rewriting of u to the t plus 1 time reversed. So this part right here means that we're plotting, or we're starting, our starting point is on the negative t-axis. And then this minus sign here means that we have a time reversal. So we're going to the left and not to the right. So anyways, our starting point is -1, which I wrote here, and it's time reversal, so we're going to negative infinity. You do want to be careful here. If you messed up where your starting point is, I did say starting point was at t equals -1, but you want to be careful on which way you put your limits of integration, because if you put them in the wrong direction, then your whole output will become negative rather than positive like you intended. But when you're working a stability problem, it doesn't matter because you're just trying to make sure it's less than infinity. So if it's infinity, negative infinity or infinity are both conditions for instability. Anything that's not infinity or negative infinity are stable. So if you do mess up your limits of integration here and get them backwards, it doesn't matter in this specific case for stability problems. Hopefully that makes sense. All right, so anyways, this integral is straightforward again. It's just a exponential. So when you take the integral of this, it becomes 1/2 e to the 2t, and then we evaluate that at the two limits of integration. So we just plug and chug, and I put my -1 time 2 times -1 is -2. 2 times negative infinity is negative infinity. And then evaluating this quantity here comes out to 1/2 e to the -2, which is just a number, minus 1/2 times infinity. So what did I do here? What did I do here? Oh, I'm sorry. This is negative infinity. Negative infinity. So my handwriting sucks right here, but this is negative infinity times 2t. So you have e to the -2 infinity. So e to the negative infinity is 0. So I missed my little negative sign here, but this evaluated to 0. So this whole thing comes out to 1/2 e to the -2. Which you can stick that into a calculator. It comes out to just a single number, which clearly is less than infinity, and this system is stable. So let's move on to another example. And this is kind of funny. I tried to pick an example that I thought was going to be unstable, and then when I worked through it, it became stable. So I had to pick another example after that to find to find a real unstable one. But anyways, let's go through this example real quick. It's pretty quick and easy. This is example 2.29f from the textbook, where h of t equals t times e to the -t times the unit step function. And this one will be kind of cool or easy because the unit step function is default or normal. It doesn't have any modifications to it. So we know that this thing turns on at t equals 0 and then remains on to infinity. So anyways, we stick this inside our definition, which I've done here. The first thing we're going to do is have our unit step modify the limits of integration, which I did here on the next step. So this system turns on at 0 and goes on to t equals infinity. The next part is the most difficult part if you are not current on your integration by, what's that called? Integration by parts.
Yeah.
Me, personally, I use an integral calculator from the internet. So I actually didn't do this by hand. I highly recommend it if you want to get lazy. I don't really think most engineers do integrals by hand these days. But anyways, that's neither here nor there. I can show you the website in a second that I used. But anyways, the integral turns out to be negative quantity t minus 1 times e to the -t, and we evaluate that at 0 to infinity. So then I plug this in, and we get our first limit of integration goes into t, so that here and here, and then our second limit of integration gets plugged into t here and here. Then we plug and chug, so we have e to the -infinity becomes 0. 0 times infinity is 0 still, so we have that here, and then e to the 0 is 1 times 1 becomes 1. We have a minus here, so minus there. So minus becomes positive, so we end up with the final result of 1. This system is stable. 1 is clearly not infinity, and that's stable. Let me quick show you. It's over on my second monitor, so you can't see it right now, but I'll just drag it over into it. This is the website I use to evaluate integrals. It's really awesome. Oh, that's not the URL, so let me just, well, I don't want to refresh it because if you scroll down, you can input your what you want to take an integral of, hit go. There's options here. You can change your variable of integration. You can put in your bounds to do a definite integral versus an indefinite integral. If you leave these blank, it will do the indefinite integral. You can even do the complex plane. You can even do, if you have a really, really complicated integral, this machine here, this website does this both symbolically and numerically. If you know it's going to be a really difficult one that might mess up the server that evaluates this symbolically, you can just have it do it numerically only, which is very useful if you want a quicker answer. And then when you hit go, it scrolls you down. This is your input. This is what it spits out as the answer, and it's kind of cool. It does remember to add the constant of integration, and then it gives you some plots too. By the way, this is your manually computed antiderivative, and this is your antiderivative computed by Maxima, which is really just a simple way of saying that I was using a numerical method. And then it gives you the graphs, and you can zoom out. It's a pretty neat website. There's a companion website that's a derivative calculator. You have a link up here. And I feel like I am selling this now, so I'm going to stop talking about it because I don't own this company or anything like that. And let me show you the URL. www.integral-calculator.com, so it's pretty simple. All right, let's get rid of that and get back to this class. So we have one more example, and then I'll stop talking. This is the example, problem 2.29b from the textbook, and this is finally a continuous time example where we have a not stable system. But let me not jump ahead and actually show you how I evaluated that. So from the textbook, it's h of t equals e to the negative 6t times a modified unit step, 3 minus t. So we stuck this into our definition of stability, and then we used the unit step here to modify our limits of integration, which is always the first thing we do. First, I rewrote this just to make it make more sense to me. So I rewrote it. We can clearly see that we have a starting point of t equals 3, and then it has a time reversal. You can see here. So we're going from negative infinity to 3 is our limits of integration. So I wrote that here. And just as a reminder, if you mess this up and get your limits of integration backwards, you're taking the negative integral instead, and it doesn't change your final point of, you're basically just determining if this is infinity or if it's not infinity. So plugging through this integral, this one's a very easy, straightforward integral. So you just have minus 1/6 times e to the 6t calculated at these limits of integration. So I just plugged them in. My 3 went here, and my negative infinity went here. This is where we finally see something blow up to infinity. So evaluating this, negative 1/6 times e to the negative 18. That is just a number. So that part is just a number. But the second term, that's the worrying part. Negative 1/6 times e to the infinity. This isn't a negative infinity, this is a positive infinity. So this blows up to infinity right here. So negative 1/6 times infinity is still infinity. And a constant minus infinity is still infinity. I guess that becomes negative infinity. So this thing is unstable. This whole thing evaluates to negative infinity. I forgot my negative sign again. Actually, no, it is positive infinity because you have a minus sign and a minus sign, so that cancels out to become positive. So yeah, anyways, this is a positive infinity, and this is unstable. That is literally per the definition. It's unstable. So this is what it looks like. Now, you could build this in real life, except that in real life, we can't ever make it go to infinity because you'd have to keep the system on until the end of the universe. At some point, something's going to stop it from blowing up to infinity, whether it heats up and burns out, or if it's like a microphone up to a speaker, the speaker might get louder and louder and louder until literally the membrane of the speaker itself rips, and then the speaker is broken, or any other method that would happen in real life to make the system break or stop. So you could build it, but it would be impractical or inefficient and a waste of your time and resources. But anyways, I hope that answers the questions about stability. And this whole lesson was for stability, and I didn't really prepare notes for anything else because that was the only topic that was mentioned in Piazza. So we're gonna switch over to whoever else is watching, see if they have any other questions, and if so, we're gonna try to answer them in real time. Although I like to make notes beforehand, but forgive me if I have to solve, like take 15 or 20 minutes to solve a problem before I talk about it. Anyways, yeah, whoever is watching, take the floor if you have a question.
Hi, I have a question. I was hoping we could go over Fourier series, especially discrete time.
Fourier series?
Yes.
Okay, so Fourier series is a week 3, chapter 3. So Fourier series coefficients specifically. So Fourier series is you're taking some signal and you're decomposing it into these weird coefficients that somehow represent like a superposition of a bunch of sine waves, right? So a Fourier series is a precursor to Fourier transforms. If you've gotten into your chapter 4 or week 4 material yet, stuff that you're going to be learning after the midterm. Fourier series was developed before the Fourier transform. But anyways, the Fourier series can be applied to any signal that is periodic. And no matter how complicated the signal is, if it is periodic, it can be decomposed into a bunch of simple sinusoids, which is quite useful for engineering and for building things. So we have here the definition. The first thing we want to do is make sure that our input has a period. So we learned in our chapter 2 stuff how to determine if a period is, if it has a fundamental period or not. Let me jump over there real quick. Maybe that's chapter 1.
Yeah, first you got to determine it's periodic, and then determine that.
Sorry. If we're talking about discrete time, something is not periodic if your n naught is non-rational, or if it becomes irrational. So here's the note. I'm looking for it right now. I think this is it right here. So your discrete time signal is periodic only if and only if omega naught equals 2 pi m over n. Yep, and it has to be rational. If things cancel out and you get an irrational number as your result, like pi, or e, the natural number e, or any other irrational number, it's not periodic. And the reason for that is you haven't learned it yet, but it comes in later in the course. But it's because of your sampling rate and aliasing. Just remember that for later. But assuming that it's not aliased and you have the right intervals for your samples when you're taking samples to create your discrete time signal. I'm getting off on a tangent. Let me go back to Fourier series real quick.
So if you tried to evaluate a Fourier series, like if you tried to convert it and it wasn't periodic, what would happen? Like, would you get a nonsense answer, or would you get an answer that's just wrong?
You would get a nonsense answer. I haven't actually plugged and chugged and gone through a problem like that, but yeah, you would get a nonsense answer. It would be inconsistent. Something about it would be inconsistent. Either it would blow up to infinity, or I'm not 100% sure because I haven't actually worked through a problem that that did that. But
in the exam, you'll see the little top. It'll say Fourier series. Usually the topic will be above the question of the exam, so you don't have to go, okay, this signal I can use Fourier transform. This signal I have to use Fourier series. This signal I have to use Laplace. The question specifically asks, perform the Laplace transform, perform the Fourier transform before the Fourier series. So,
actually, I got an answer for you. It would not be an inconsistent or nonsensical answer. What it would be is just a plain wrong answer. It would look like an answer, but it would be a plain wrong answer. So I just went through it in my head. The definition of aliasing, which you have not learned yet, you'll learn in week 5, I think, is when you're taking samples of, let's say we have a thermometer and you want to take samples twice a day, and And you're taking samples to just look at the weather patterns of your, trying to come up with an example on the top of my head, and you're looking at the weather of your area or something. If you took samples once a year, you would not get an accurate picture of your weather, because once a year is not often enough. If you took samples maybe once a month, that might not be accurate enough because weather changes daily. So you want to take samples at least daily. So twice a day is good. Once a day might be good enough, but twice a day is better. 50 times a day is even better than that. So anyways, if you don't sample enough, you get a misrepresentation of your system. So if you go to do a Fourier series on a system that isn't sampled at a high enough rate, you're gonna get coefficients out of it. You're gonna spit out an answer. It will just plain be wrong though. It won't represent your system as a whole. It will just look like some other system. So try to remember this when you learn about aliasing later. I actually have a really cool picture. Well, the course in the textbook and other resources on the internet have really cool pictures of what aliasing is. Let me see if I can Google that real quick and pull up a picture that kind of explains a little bit better. The Wikipedia page is usually pretty good for that. So here we are. Let me pull this picture up, and I'm going to swing it over here. So this is aliasing, and if you let's say this blue curve here. Let me make it. Oh, I can't make it bigger. This blue curve here is your signal, and this signal represents some system. It doesn't matter what it is, but this, you can see that we have a frequency that is much higher than the signal behind it. The signal behind it, this brown signal, this is what it would look like if I sampled this blue signal at not a high enough rate. If I sampled every, let's see, one increment, and then I plotted that and tried to extrapolate what function created those points, because keep in mind that when you're taking DT, a DT is discrete time, you're taking samples. That's what these black dots are. You're taking samples, and if you have just a picture of just the black dots, and you don't know what the underlying signal looks like, you might just draw a line from dot to dot, which is what this brown line does. And then once you draw straight lines from dot to dot, you might be like, oh, this looks like a sine wave, and then you'll just make a curve. You make your curve plot. But that is a misrepresentation of what the actual signal is. The actual signal is this blue line, which goes at a much faster rate, a much higher frequency. So let's say I took the Fourier series coefficients of this brown line, what I thought my discrete time samples were representing. It's going to spit out some number. You're going to get coefficients, however many they are, and it's going to represent this sine wave. But it's going to be plain wrong because your system is this blue line. Does that make sense?
It does. So you'd get an answer, but the answer doesn't represent the system. So
Yes.
It's not really a Fourier series at that point.
Yep, and that's what happens if you do the Fourier series on a system that you're
not really periodic.
Yeah, it's not considered periodic.
Thank you.
Yep, no problem.
Okay, so Theron, sorry, I probably really screwed up your name. He had a question, or she, I'm not sure which, had a question on Piazza about the relationship between X of JW, Y of JW, and then H of JW, that kind of thing. So let me present and share. What did I want to share? So this is definitely not on the exam for this exam. It'll be on your final for sure, but I don't think it's so much for this test coming up. But it is a pretty important concept for the course, so I kind of wanted to touch on it. Let me see, screen 3. Yeah. So eventually you'll be getting questions like this, the Fourier transform, and you'll see this X of t, H1 of t, and then you'll have the output Y of t. And they'll give you 2 or 3 of these signals. Like if we cut this off and it was just this portion of just the X of t, the box, and then this would be the output. They'll give you 1 or 2 of these signals, or 2 of these signals, and ask you to find the other one. I have another problem that shows it better. Let me see here. This is Laplace, so don't get too worried about it. But the relationship is the same for Laplace or Fourier or any of the other ones. Is the y h of s is, or h of jw in this case, would be y over x. So this is basically convolution in the frequency domain. So we get to use just straight up algebra, multiplication and division to do it in the frequency domain. So this was an actually pretty difficult Laplace problem. So I gave it to the students last semester to test them up. But basically, you're given the two in the question we're given x of t is the unit step function, y of t is this function here. We perform the Laplace transforms and do the algebra, and that's how we derive the h of s. The h is usually the impulse, which is the impulse response of the system. So that I should have learned week one. The impulse response of the system completely describes the system. So once you have the impulse response, you can put in any input you want, and you'll be able to know the output of that system. So that's kind of a look of where we're going and the relationship of what's coming up. I hope that helped, Theron. Or we can talk about it afterwards too if it confuses you. But like I said, that's more of it's coming up later. Not really need to worry about it too much for this test, but they've kind of hinted at this relationship. But you'll get real familiar with it after the midterm. Anything else anybody wants to cover?
Yeah, so I had a question maybe about the review number 5.
5?
Yeah, convolution, discrete time, two connected linear time invariant systems. So I guess maybe what I'm having trouble with is figuring out how to track the leading edge of the impulse through the I guess through the other signal, because I think that's basically it seems like once you figure that out, the system or the problems become more straightforward. But I think that is kind of what I'm struggling with, is one, figuring out what the leading edge is, and two, like once it moves through once you move it through x of k, I guess in this example, how you set up what each point is. So in the key, it has, when n plus 1 is less than 0, it's this. I'm assuming that's kind of the point where there's no overlap. And then when n plus 1 is equal to 0, then you have another output for y of n. So I think that part, maybe the first 3 I can kind of get because it's represented graphically. But maybe for the third one, it's a little bit difficult for me to wrap my brain around. And then
yeah, I had a hard time with direct time convolution too. It's not it's not easy. I did this problem last semester. I got it up on the screen. So basically, I did it graphically here. For convolution, you're going to put one just a straight up transfer to the k domain, and the other one's going to have an n minus k. So you have the lead is n and then n minus 1, and then so if n plus 1 equals 0, we have some overlap. So for n plus 1, I kind of tried to color code it too when we did it. You have this h of k is right here in the red dots, and you have the part you're moving right here in the blue dots, and then you just kind of run through all the variables of n. So if n plus 1 equals 0, so at that point n equals 1, and then you have an overlap of 1 and 1 to equal 1. Then if n plus 1 equals 1, you have 2 overlap. The best, and keeping track of the leading edge is a hard thing to be to keep track of, I guess.
Yeah, yeah.
And that's what this little explanation up here is.
Yeah.
I
guess maybe setting up the leading edge, but it looks like once you plug it into the n minus k format, it kind of spits out what your leading edge is. Okay. And then from what I guess from what I can tell, basically your leading edge goes through, I guess it depends on the input, but 3 kind of distinct points. It seems like one is where there's no overlap, if that's the case. The second is right where they meet, which is sometimes at the origin, but not always.
Yep.
And the third is kind of like at the edge of
they kind of line up perfectly. It depends on how much over you're gonna have them where they meet, and then you're gonna keep pushing through for each value until they separate again over here.
Okay. And then once the trailing edge or once the leading edge separates, once the leading edge separates, that's where there's no overlap anymore, and you're done basically at that point.
Yeah.
Okay.
And then you have all the values, and just line them up here, and then you can just put them into a step function or a delta function that represents what numbers you've just collected.
Okay.
There's a in the week 2 tips video, I think that guy is really good with convolution, and they're kind of long or lengthy, about 20 minutes a piece, but they are excellent. They as far as the as compared to the lecture videos or whatever, I was kind of completely lost, and then I watched all those videos, and I was like, oh, and the guy's got a whole series. I'm not sure of his name, but he is very good at explaining it. He's got a whole. You can look at the whole series of them, and they're really good.
Okay.
Well, this is we got 3 pages for this part B.
Yeah, it's pretty intense problem.
Yeah.
Okay. And it looks like at least in the review, maybe the method 2 method is the
math method.
Yeah, the simpler way to do it, kind of the direct.
Yeah, there's the method 2 is just 3 lines instead of 8.5. Yeah. There are some equations that are easier to do graphically. There are some that are easier to do with math.
Yeah.
Especially if you got a bunch of delta functions, it's probably just easier to do with math. Sampling.
Sorry, I guess maybe that's one question I had is it going to be the case maybe in this course that these equations that represent the impulse response and the inputs are relatively simple to graph, like punch into a graphing calculator and see what it looks like? Because I think that's kind of the tricky part, is figuring out what it looks like and then figuring out what the unit step does to it.
I don't remember having any trouble graphing any of the problems on the exams.
Okay.
I'm trying to think of any of them that would trick me up. I can't think of. I mean, if I was required to put a graph down, it wasn't tough. I remember that.
Okay.
So you might see something with the e's, or you might like an exponential decay, or just a square box,
right?
Or a series of pulses. But nothing I can. Like I'm not even. Yeah, I don't even remember doing an exponential. But it's been, I guess, a year now since I've taken this class. But
okay.
Been a TA in it 3 times now, so
Hold on.
Figure I'd be good at it.
Let's test that.
Well, there you go.
Yeah, I think that's all I've got. I haven't gone through 8 and 9 in the review, but those look relatively straightforward as far as finding out the coefficients.
We could. I think I've got 9. That's 7, so it's being the other one. Waiting for response. Always. My computer's run super slow lately, huh? Yeah, mine was not. It's on 2 pages, but so it's look at 9 is basically find the Fourier transform and use the geometric series, and that gives you that form. A Fourier series, not transform. I'm sorry, I misspoke there.
Okay.
So you're given h of n. Let me see the question. I don't remember the question. I'm not sure I have it. No, I don't. Midterm review. That's not right.
Yeah, it was essentially taking that impulse response, asking what was the frequency response, and then if you had certain Fourier series coefficients, what were the Fourier series coefficients of the output, and then what was the representation of the total output.
Oh, so it does have that relationship of H and Y.
Oh, there it is. Yeah.
Yeah. So, yeah. So I guess the H and Y, that relationship is introduced.
Okay.
In fair game. So yeah, first one you just compute the impulse response. You to take that and put it into your. Did I close that? Or equation, term review. Roll down. That's so you take that and you plug it in here and wait. So this is what we're doing here to find the coefficient.
Okay.
It's that equation, the A of K's. On the video, I'm a little more refreshed and familiar. So
Sure.
the other YouTube video I posted, it would probably be better to watch that, and if I rewatched it.
No problem.
To remember what I was doing there. But it looks like I just throw it in a geometric series and get this form.
Okay.
That gets, and then get the coefficients for that. So okay, there's I must be doing this one. H of E of JW. This equation.
Yeah.
For part 1, and then this equation for part 2, then probably this equation for part 3.
Okay.
So anyway.
Okay. Thank you.
All right.
Does everybody understand the difference between? I don't know if my screen's presenting right now, but I guess I need to.
Can be.
How do I just click my thing here?
There you go.
Oh, okay. All right. So does everybody understand what these things mean? So like what an AK is versus an X of T. And is anybody confused by like the apparent nesting that we have here with an AK inside the XT and stuff? Or does that all make sense to everybody?
So for my understanding, it kind of looks like we kind of find the AKs first in the problems that we've been doing. And then we kind of go back and find what the total representation of the input is.
Yes.
I'm not sure if that's correct, but.
Yeah, that's correct.
Okay, yeah, so it does seem kind of out of order here if you're going to go like step 1, then step 2.
Yeah.
I've just kind of been trying to picture it as, okay, just first do step one, which is AKs first, and then once you know that, then go back to finding what exit T is.
Yep. Yeah, so the AKs, those are your Fourier series coefficients. But the Fourier series coefficients by themselves don't represent the signals. You have to add something to them to make them like physically realizable, I guess is the way I'm going to put it. But yeah, the AKs by themselves is literally just a coefficient. They just go in front of other terms, you know, where those other terms are complex exponentials that are at a certain frequency where you have your omega naught. Does that make sense? So I have a really good video that I usually link in the 4th week. I think actually I linked it already, or James did. Let me double check. But this video is a 3 blue or a 3 brown 1 blue video on YouTube. It's like they have a channel and they make really awesome videos about science and math and engineering and stuff, and they explain it in very intuitive ways. But anyways, they made one for Fourier transforms, and that's why I usually introduce the link to this video after the midterm. But it definitely is very useful for week 3 material, talking about the Fourier series, because it, you know, you're essentially doing the same thing. You're decomposing a signal into sine waves. That's literally all the Fourier transform and Fourier series do. Let me see if I can pull up the link real quick. I guess. Hey James, did you post anything about the study tip stuff for week 4 yet?
It should have been, I thought, first of the week.
Oh, here they are. So is this that? Let's open it and see. Nope. So I'll post it after this video, after we're done. But take a look at this video. It's about 20 minutes long, and it's purely conceptual. It doesn't teach you the mechanics of solving problems or anything like that. Purely abstract and theoretical, but it's super interesting and might make this Fourier series stuff more palatable.
Did you link it down below to the next comment?
Where? Back in Piazza?
Yeah.
Oh, yeah, yeah. Here it is. I did do it. I thought I did. So, start at the beginning. Oh, I gotta watch an ad. So yeah, this video right here, truly amazing video, and definitely watch it if you haven't. If you have the 20 minutes, it's a long video, but it's super interesting, and might clear up what a Fourier series is actually doing. But yeah, does anybody have any other questions or anything like that?
I wonder if we're going to get a copyright strike for streaming another YouTube video on my YouTube channel.
I hope not. It's in the public domain.
Well, if there's no other questions.
Oh, sorry, one more.
Oh, yeah, go for it.
So regarding causality, I think sometimes I think I get it, and then sometimes I go through a problem and it's apparent that I don't. But I'm basically my idea thinking about this is that if it's causal, then it essentially doesn't depend on any
negative time.
Sorry, say again.
Negative time. It doesn't have any negative time in it. You got a time reversal or something where you go back in time.
Yeah.
Then you're not causal.
Then you're not causal. Okay. So if there's a unit step and it's not time shifted such that it's on in negative time, then you're not causal.
Ooh,
you said that backwards.
Oh.
If it's in negative time, that means it's not causal. So what you just said is a not causal system. Okay.
So if it's something, let's say, that's on from negative infinity to 1, then it's not causal because it does not depend on future inputs.
No, because it does depend on future inputs. So negative values in time are our future inputs.
Negative values.
So, like, you take your input signal, right, and it starts at 0. So, if your output happens before the input, it's not causal.
Yes.
Right?
Yeah.
Yep.
Okay.
So
Okay.
the reason why negative values represent the future instead of the positive axis is because let's imagine that I have a system in front of me, and I just hit the power button. The system is on now, and now I'm collecting. Let's pretend like we're talking about a discrete time system. I hit the power button. The system's now on, and I am now traveling along the x-axis as me and the system go on into the future, right?
Mm-hmm.
So we're collecting data in real time at every interval. We're taking a sample, whatever that interval is, and we're plotting this on a graph. Well, as we move into the future, by staying in the present, we're plotting on this graph. We plot by convention on the positive x-axis, right? Does that make sense?
Yeah.
So if I wanted to take a point from the future that hasn't happened yet, because I'm only in the present, that's going to be on the negative axis. Does that make sense?
I think so.
Okay, so let me explain something else about causality. You cannot physically build a non-causal system that acts in real time. That's the underlying part right there. That acts in real time that wasn't mentioned in the course.
Okay.
Flux capacitor.
However, what's that?
They said unless you have a flux capacitor.
Oh yeah, unless you have a time machine. But you can build a non-causal system that doesn't act in real time, and we do that all the time. In fact, you guys did it in Lab 1. So a non-causal system that is physically realizable in real life requires that you have pre-recorded the signal and have it stored. So like when you record well, we're recording this video right now. If I wanted to, I could play this video backwards. Playing this video backwards is literally multiplying your input signal, the video, times a unit step that is time reversed, that has a negative t value. Does that make sense?
Yeah.
So I could play this video backwards. I just have to record the video first and then store it and then apply the system to it and then make the output.
I have a question about that.
Okay.
Would that also apply, like, if you have buffering? Like, so if you buffer 3 seconds, could you then make a non-causal system that acts within those 3 seconds, or do you have to have the whole thing recorded?
Yeah, absolutely. You can have a system that relies on inputs from the buffer. Oh, wait, hold on. I gotta think about this. No. So what a buffer would be doing is storing past data that you then use in the present. It doesn't take data from the future. So that does seem confusing, doesn't it? Because that kind of negates what I just talked about with a recording. But with a recording,
well, the recording you're playing backwards, whereas the buffering is not memory, it's requiring stuff from the past.
Right. Yeah. So a recording, you have the entire signal at your disposal, and you can move along the timeline at any point. A buffer, you can only, like the buffer is collected in real time still. That's going to be hard to explain with words. I have to really ponder this one.
It has more to do with the direction of time rather than how much time you have available. Is that right?
Yeah.
Okay.
The direction of time. So in this in this universe, we travel forward in time. But in a computer where a video recording or sound recording was stored on a hard drive, you don't have to define a direction of time. You just can pick a time, and then move in any direction that you want. In a buffer that you collected in real time, you still are moving into the future, just like you would be without the buffer. Does that make sense?
It does. So you'd have to basically you have to know where your end point is before you can get to the beginning because you're going backwards.
Yeah. Now you can do reverse time stuff inside the buffer space. That is possible. So like, for example, if I had a microphone attached to a speaker, like a megaphone or something, and it stored 3 seconds of, if it stored up to 3 seconds worth of recorded audio, you could then play that 3 seconds backwards in the next 3 seconds in the future. Does that make sense? But as you're playing it, the buffer is being overwritten. So then it causes a problem.
Yeah, so the longer your signal is, the more you would have to buffer in order to go backwards.
Yeah, and then with the buffer too, the buffer, since it's constantly being overwritten, is messing up your ability to manipulate it. So yeah, that makes sense now. Okay, so we need to define buffer real quick. So there, you can have in real-time buffer, and you can have a stored on a hard drive type buffer, where an image is stored and then overwritten all at once. Does that make sense? So an in real-time buffer, as you're recording, that buffer is being overwritten continuously. Therefore, you can't use all the data that's in that buffer. Like, you can't choose a point in the buffer that is about to be overwritten. You can only use the data points in the buffer that are furthest away from being overwritten. Does that make sense? Versus a snapshot that's captured all at once and stored on a hard drive, like in a digital format. Well, one, you can store that indefinitely until you choose to overwrite it. That is the situation where you can record, where you can manipulate it and do a negative time shift too. Because none of your data points in a stored image will be overwritten. So we have to be careful with our language and how we define what a buffer is. If a buffer is in real time, like an analog buffer, then yeah, it's going to be overwritten as you're playing it.
Thank you.
Yep, no problem. So no, Jeff, you're the one that asked about causality to begin with. Did we answer your question at all yet? I kind of forgot what your original question was.
Yeah, I think so. So as a kind of an example, so at work, I deal a lot with engine control units. And sometimes we have certain signals that are stored in memory. So let's say you turn the car off and everything that's in volatile RAM gets erased. So the next time you start the car, all of it basically starts at 0. Mm-hmm. But some values, they hold the previous value, like a temperature or something like that, from the previous time the car was on and running. So in that sense, for that particular parameter, before t equals 0, which is essentially when you would turn the car on or turn the ignition on, there is already a value present that is not 0. So, and that value would be an input into something else. In that sense, because before t equals 0, that signal is not 0, would that be an example of a non-causal system?
I would say that's causal because that signal was taken from the past and used for something in the present.
That is causal.
Yeah.
Yeah, the actual T0 would be like when the system started existing.
Okay.
So, yeah.
Yeah, so in your engine control units, they're never taking a piece of data or parameter from future driving of the car. It's always the past. So it's still something that's from the past.
Got it. Okay. And so future driving is the negative axis. I guess that's where it kind of like breaks down for me, because for me in the future seems like something that's coming ahead on the positive axis, not from the negative axis.
Yeah, it is confusing, but you just got to think about, you have to be the system. Instead of thinking as you as an observer of the system,
mm-hmm.
Go from the mindset of what the system sees.
Right.
When the system first turns on at t equals 0, it starts recording. I mean, it starts like doing whatever that system's meant for. It starts doing the things. And if we're talking about discrete time, maybe it's taking samples of stuff.
Right.
It will start recording those samples in whatever storage medium it has as that object goes into the future, because it's existing in this universe, right? It's traveling. Right. We're all traveling into the future.
Right.
Via the vehicle of the present. So when you are looking through the eyes of the machine itself, and you turn on and you start recording, you're plotting those points on the positive x-axis.
Right. Yes.
Okay. So nothing ever gets plotted on the negative x-axis.
Right.
At any point in time. Therefore, that whole region of your graph, the whole negative x-axis, is reserved for the future. And things close to the zero axis, to t equals 0, like t equals -1 and t equals -2, those are pretty close to 0. They're certainly closer than t equals -100. Those are closer to the present than larger values on the negative t-axis.
Okay.
So if you wanted to plot something at 100 years in the future, you're going to be plotting way, 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 way to the right.
Right. Right.
If you wanted to plot 1 second in the future, you're going to go to the right of the zero axis just by a little bit.
Right.
So as you, the machine, looking through the eyes of the machine, as you are traveling into the future via the vehicle of the present, you never reach the negative axis at any point. Right.
Right.
And that's just how our universe works.
So if you did have a flux capacitor, then you could skip back to the negative axis and put something there, which would influence the output as you move toward or move from the zero point.
Yeah, I guess.
Okay.
Well, you'd move forward in time to influence the output presently.
Okay. Okay. I think I can work with that. Yeah, I mean, the review says basically if it's 0 for all t less than 0, so for all negative time, that's pretty straightforward definition, which is kind of easy to understand. I think I'm just struggling with it conceptually. Maybe because it's difficult to bring such a system into the...
Yeah, they don't exist.
Yeah. Or hard to make an analogy.
Cool.
Okay.
Anybody else? Virginia, you got anything? Jeff? Cecilia? Anybody? Oh, this is good. Cool. I'm gonna open the chat. I missed it. Oh, Theron linked a video in the chat that helps them. It's from one of my posts, so. Cool. Well, we will be doing another one of these before the final two, so if you guys, as we go through and something doesn't click or, you know, keep a list, keep us honest. We want to help as much as we can. We just need to know what we need to help with. So.
Yeah, whatever subjects you guys have trouble with throughout the second half of the semester, just let us know on Piazza, like a week ahead of the final, and we'll, just like I did earlier with the stability lesson, I'll make notes, I'll go through problems, James will do the same thing probably, and then we can go through anything and everything that you guys talk about. So asking questions in real time is great too, just like we did just now, but it's harder to really get into solving problems specific, like conceptual questions are easy to answer in real time off the top of our heads, but solving problems, let us know those types of questions first so we can prepare examples and like go through the mechanics of it.
Mm-hmm. The stuff is hard and we forget it, and sometimes we have to look stuff up.
Yeah, and I don't want to make you guys sit for 30 minutes while I solve a problem before I explain how I solved it in real time.
Cool.
But yeah, thanks for joining us, guys.
Podcast.